Hey guys, welcome to my channel. I don't know how you got here, but I do hope that you'll stay until the end of this video because in this particular video, we are going to talk about the Pythagorean Theorem. Specifically, we are going to derive how the Pythagorean Theorem came to existence, okay? So let's take a few steps back. Let's talk about when we can use the Pythagorean Theorem. So the Pythagorean Theorem is only used on right triangles. Okay, it can only be used on right triangles. Now, what exactly is a right triangle? A right triangle is when two of the legs form a 90-degree angle, right there. And we're going to call this vertical length, length A, and we're going to call the horizontal length, length B. And the final line, which is typically the longest line of a triangle, except in the cases of isosceles triangles, which we're not going to talk about right now. We're just going to stick to the right triangles. In the case of this particular triangle and most triangles, the longest line is known as the hypotenuse, which we're going to label as line C. So through the Pythagorean theorem, we can determine a relationship between these three lines. Okay? And that's when we use the Pythagorean theorem. So let's go ahead and erase that. Okay, so how did the Pythagorean theorem come to be? Well, it all started with this ancient Greek dude named Pythagoras. Now, Pythagoras, uh, he likes to you do a lot of critical thinking. Okay, and legend has it that one day Pythagoras was waiting for his friend at their home, and he was just waiting there, and he started looking at the tiles. Okay, he started looking at the tiles on the floor because he started getting bored, and he figured, I'm gonna do some critical thinking. I just need to get my mind off of waiting, you know. Now let's assume that all the tiles on the floor were squares, square tiles, meaning to say that each side of each tile had the same length. So we're going to try to recreate the vision that Pythagoras was looking at, the scene. We're going to try to recreate the scene. So I'm going to attempt to draw 5 parallel lines, 5 vertical parallel lines. Here we go. Okay, 1, 2, 3, 4, and 5. Okay, and let's draw another 5 horizontal. 1, 2, 3, 4, and 5. Okay, so you don't have to draw this. This is just to give us a visual representation of what Pythagoras was looking at while he was waiting for his friend. Okay, now he started doing some critical thinking while he was just sitting there waiting, and he started looking at the tiles, and he's just, you know, he's thinking about the common knowledge that a square tile is when a square is when all of the sides are of equal length, like I said earlier. And, you know, in his mind, that's like, that's so basic, that's so simple. Let's try to complicate things a bit. So what happened was he looked at one tile and he said, you know what I'm gonna do? You know what I'm thinking? I'm thinking I'm gonna cut this tile in half. I'm gonna cut it in half diagonally. Okay? So he cut it in half, and then there it was. It was diagonal. And he started asking himself, how can I figure out the length of this diagonal? He just looked at it, and he's just like, wow, that's something. How come we don't know how to figure that out? So let's go ahead and start determining some things first. The first thing we know is the area of each tile, and we're going to call that area of tile square 1. Area of square 1, okay, is equal to, so all of the lengths are of the same size. That means that the area of square 1 is equal to s squared, okay? Meaning to say that all of these sides, same length, okay? And just to make it even more interesting, we're going to call this s sub 1. So s sub 1, s sub 1, s sub 1, and s sub 1. All right. Now, as I said, all of these tiles were the same size, and he was just looking at it and he was thinking, I gotta figure out how to figure out the length of that diagonal right there, okay? So he started forming a relationship to some of the adjacent tiles, and he started right here, let's say. Okay, he started looking at this tile, and he started looking at this tile. Now, why these particular tiles, you might be asking? Because two of the lines on this triangle are connected to these two tiles. So, through connecting these lines, we create the one triangle that he created from the one square. Okay? And like I said, all of these squares are of the same size. So that means that all of these lines are also the length of S sub 1. Sub 1, S sub 1, S sub 1, S sub 1. But he still wants to figure out the length of S sub 2. That's why we call it S sub 1. Because this blue length right here, this diagonal, that's S sub 2. But he established a relationship, okay? He established a relationship between these two squares and this one diagonal. Okay? Now, let's look at it even further. So, when we look at this diagonal, we created two triangles, correct? So that we could say then that the area of the triangle in this instance is equal to, okay, the area of the square divided by 2. Okay? So, you guys follow me right here? The area of this square, square 1, divided by 2, which is also equal to S sub 1 squared divided by 2. Right? Now, he still doesn't have enough information to work with because through this information alone, all we've established is that if you divide one of these tiles in half to create two triangles, then you get half the area of a square. This is not enough information to work with. So he further developed some more relationships, and what he found was he could create a second square by cutting other tiles in half. So he cut this tile in half. He cut this tile in half. And lastly, he cut this tile in half. Okay? So now he has cut in half 4 tiles. And each of those lengths are equal to the length of S sub 2. They have to be because all of the tiles are of the same size. So this is length S sub 2, S sub 2, and S sub 2. Okay? So now we have a new equation to work with. When he created this new square, which we're going to call area of square 2, okay? What happened was that became the area of the triangle times 4, right? Times 4. Okay? Area of the triangle times 4. Because why? We have 4 triangles. Okay? Now, if we know that the area of the triangle is equal to S1, S sub 1 squared divided by 2, we can plug that into this equation. So that is equal to S sub 1 squared over 2 times 4. Times 4. There we go. Okay? And if we break this down even further, so this becomes equal to 2 S1 squared, right? So what happened is we have 2 squares of the same size as the original tile. How can we prove this? Well, like I said, all of the tiles are of equal size. So if you look at these 2 triangles right here, these two right here this forms the size of the original S sub 1 squared. And if we look at these two, it forms the original size of the S sub 1 squared. So that means that this is correct. 2S sub 1 or 2S sub 1 squared is equal to this new the area of this new square. Okay? So now we have a lot of information to work with. This is a substantial amount of information that Pythagoras could work with to create this theory. So we know for a fact that the area of the new square, so we're going to go ahead and raise that to 2. The second square is equal to 2 of the area of the first square. I know it looks like a triangle, but that's an A. A and A, okay? Area of the new square formed is equal to the 2 times the area of the first square, the first tile, the original tile. And we have a lot of information that we can start plugging in now, okay? What information is that, you might be asking? Well, let's go ahead and start here with the area of the second square. The area of the second square is going to be equal to 2s1 squared, okay? And this one is equal to 2, okay, s1 squared, okay? I'm sorry, 2s1 squared, right? Okay, there's a difference between these lengths, okay? 2s1 squared is equal to s2 squared. Okay, sides sub 2 squared is equal to 2s1 squared. Okay. Now what's the difference between these, okay? When we say 2s1 squared, this length means that s1 squared is the original length used in the original tile. In this one, we have a different function. Because this one, we can divide it into 2. This one, or this one, we can't divide it into 2 because it's one whole function. So that means 2s1 squared is right here. This length right here, which is the area of the second square, which is this right here, which is going to be what we're going to now call as c squared. Okay? And if we break this down here, this is equal to s1 squared plus s1 squared. S sub 1 squared, S sub 1 squared. Okay? And the interesting thing about that is if we break these down into different types of squares, let's say this is square A, square B, and square C, we now have A squared plus B squared equals C squared. It's crazy, right? It's confusing, but I think it's awesome. It's awesome that Pythagoras was able to come up with this theory. So we can see here that the reason the 2 is s1 squared here is in apostrophe parentheses, sorry. It's because it's a different type of equation. This is 2 different numbers forming together. And here 2s1 squared is one number in itself. You see the difference? So that means that this is the area of square number 2, which is the bigger square. And this s1 squared here is the area of the first square. And we have 2 of them, which is right here, square A and square B. And when we break it down, it all becomes a squared plus b squared plus c squared. So when you look at it, you kind of want to ask yourself, or you might be thinking, well, GN, why don't we just add the 2 legs and come up with the hypotenuse? That's because that's not how the theory works. How Pythagoras came up with this theory is he looked at it as a relationship between squares, not a relationship between lines. And this is how we prove that it is in fact a relationship between squares. Because we look at this here, this is the area of the second square, which is the largest square, and this is the area of the smaller squares, which is the first original tile. It's not a relationship between the lines. It's actually a relationship between squares. Crazy, right? Let's say that you're still not, you're still not convinced. You're still like you're still looking at me like, well, how did he know that was going to work with every single situation in the world involving right triangles? Well, we can actually prove that as well. Let's go ahead and let's just clear the board here. Let's clear that up, okay? And let's go ahead and create a square, okay? I'm going to try to create this as perfectly as I can. Please don't judge me. Okay, let's go ahead and create one square, just one square, okay? And from this square, we're also going to create a square inside it. Oh my gosh. My hand is so unsteady, I'm sorry. Okay, so we got one square. And we have another, come on. Straight line, straight line, straight line. There we go. Okay, and we have another square inside of that square. Excuse me, sorry. Okay, trying to do this as perfectly as I can. That's why it's going to take me a while, because I'm imperfect, but... Alright. Oh my gosh, come on. Come on, Jian, you can do it. You can do it, Jian. Let me just give myself a pep talk. Okay, this is as good as it gets, so don't judge me. Okay. In this particular example, we have two squares. We have the bigger square and we have the square inside, okay? Now, as we all know, this is a square, so that means that all of these angles right here, right angles. All of these equal to 90 degrees. Same thing goes for the square inside. All of these are of 90 degrees. All these angles, 90 degrees. Bam, 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 bam. Okay? So I'm going to go ahead and remove those because they're going to kind of be distracting in a bit. There's going to be a lot of writing going on here. Okay. And what happened is we created 4 triangles. Okay. And since all of these are all 90-degree angles, that means that all of the triangles within it are right angles. And since they're both squares, that means that each right triangle that's formed from these two squares are of same size due to the theory of identical triangles. Okay? So that means that this length is the same as this length, and that length is the same as that length, and that length is the same as that length. And to make it more clear, we're going to go ahead and label these lengths as length A. Length A, length A. A, oh my gosh, length A, length A, okay? So all of the shorter lengths, we're going to call it length A. The longer lengths, we're going to call it length B. Length B, length B, length B, and length B. There we go. Okay. Now, for the length of the square inside, we're going to label those as length C. Length C, length C, length C, and length C. Okay, so you're following me so far, right? Now, how do we get the area of the smaller triangle? Just by using math, okay? Well, it's a bit complicated. So, in order to get the area of the bigger square, we need to get the area using the formula s squared. So let's go ahead and label, in this instance, we're going to label the bigger square as square 1. And that is equal to s sub 1 squared. So this is a new equation. Don't mix it up with the first one. These are just variables, okay? Now, s1 squared. So what we have to do is we have to look for s1 because s sub 1 is our length. Now, how do we find the length of this square? Well, it's simple, a plus b. Meaning to say that in this particular instance, we have to add a plus b. A plus b. Then we can square it. Okay? So the area of square 1 is a plus b squared. Those parentheses are very important. Remember, they distinguish the difference in how to do the order of operations. Okay? And in the order of operation, all of the things inside the parentheses goes first. Everything else is outside, right? Otherwise, what would happen is we'd make it b squared plus a. So that's not how it's going to work. That's the same situation as what happened earlier on our first example. So that's the first thing we know so far. Now, the area of the smaller square, which we're going to go ahead and label as a squared 2, is equal to, okay, s sub 2 squared. Or in this instance, it's s sub 2 is equal to, whoops, sorry. Let's go ahead and label it here. S sub 1 is equal to a plus b, okay? S sub 2 is equal to c. Okay? So that means we're going to plug in c for s sub 2, which equals to c squared. Okay. Now, this isn't enough information yet, because what's going to happen is we have to subtract all of the excess area in order to get the area of the square, the smaller square, right? So what happens is we have this equation, s square 1 minus something is equal to c squared. Or, sorry, is equal to the area of the second square. Okay? So what is this question mark right here? How are we going to figure that out? Well, we have our 4 triangles. And we need to get the area of each of those triangles in order to find the the area of the second square. So we know that the equation to find the area of a triangle is equal to 1/2 base times height. Base times height over 2. Okay? And we can plug that into this formula because we have, let's take one of these triangles. Let's go ahead and bring it down here. Sorry. Bring it down here. And let's say that the letter A will be our height, okay? And the letter B will be our base because it's on the base, right? And this is the height. Common sense. Okay? And why is it base times height? Especially for right triangles, it's very easy to understand because if you cut base in half and you rotate it over here, what you get is a rectangle, okay? Bam, it becomes a rectangle. That's why it's 1/2 base times height, because you're basically cutting the base in half, rotating it over, and you're forming a rectangle in order to get this length or this area. So that means that the area of these 4 is equal to the area of the triangle is equal to base times height, right? Which means that's equal to a times b over 2. Okay? But since we have 4 of them, we have to times it by 4. So the whole area of these 4 triangles has to be times by 4. So we derive it 4ab over 2. And these two cancel each other out, which makes it equal to 2ab. Crazy, right? It's math, and I love it. Okay, so that's our formula here. That's what we're going to plug in right here. We're going to plug in the area of a triangle. Now we have everything we need to work with. We have the area of square 1, which is a plus b squared. So we can plug that in right here. A plus b squared. Okay? Don't forget those parentheses. Okay? Minus this right here, the area of the triangle, 2ab. We're going to put those in parentheses because we don't want to confuse them all. It's going to equal the area of the smaller square, which is c squared. Right? Right. Now, if you guys remember the FOIL technique, because we can't just square a plus b. We have to use FOIL, which mean what does FOIL mean? If you guys don't remember, let's go ahead and do a quick quick review. FOIL stands for first, okay, outer, inner, last. So what does that mean? Basically, a plus b squared is a plus b times a plus b. So let's go ahead and derive this first. A plus b times a plus b. This is what a plus b squared is equivalent to, okay? So we have to do the first, which is a squared, because we have a and a. A squared, okay? Then we do the outer, a, b, okay? So we add those because positive a times positive b is going to be a positive number, okay? Then we do the inner, this right here, b and a, which can also be equal to b a times b, okay? With me so far? And last we do the outer, which is b and b, b squared, okay? And in this particular equation, we can bring these two together, and we get a squared plus 2ab, okay, plus b squared, okay? Now, we put this into the equation. So we can go ahead and make it complete. Minus 2ab, which is the area of the four triangles that we created, 1, 2, 3, 4, is equal to c squared, okay? And we have a positive 2ab and a negative 2ab right here. So guess what? They cancel each other out. ab, 2ab, 2ab, gone. So what do we get? A squared plus b squared equals c squared. Math. It's. I don't know. I love it. It's amazing, the things that we can accomplish with math, and yeah, it's a lot to absorb, but it's one of the beauties. If you work in a field like architecture, working with triangles, it's just the best feeling, because the thing about triangles is they work in all shapes, you know. They work in all shapes and all forms, and you know, even like the way that the legend says Pythagoras came up with the formula. He had to break a square in half to create two triangles. So that means through breaking shapes into different triangles, we can accomplish a bunch of crazy new things, you know. And in architecture, especially, if you notice, if you notice when you work with software such as CAD or SketchUp, and you make circles, for example, it doesn't make perfect circles, right? What happens is it makes broken down circles, circles that have segments, meaning to say, like, sometimes CAD will break down circles into octagons or hexagons to make it easier to read. But what basically all these programs do is it just breaks down the circle into more smaller and smaller and smaller lines. And the crazy thing about that is when you connect them at the center, they still make different triangles. It's the same thing with ellipses. Break it down in the center, they just create more triangles. So they keep creating infinite amount of lines. And squares, rectangles, whatever shape, you name it, it's all triangles. It just all keeps going, you know, the basic, you know, if when it comes to basic things, basic forms, uh, we look at them, but we don't really take into consideration like how it all works, because you know, it kind of limits our ability to create solutions, you know, design solutions, if we're not able to figure out where they all started from. That's why, for me, I believe that, you know, math is a good foundation for up and coming architects or people that want to design, because math also plays, like, aside from creating space, it creates psychological effects as well, because through math we develop, like, the way that colors work, the way that lights work, and the way that all of these things work. And uh, it's all just a matter of time before it all becomes this derivation into numbers, you know. Anyway, I'm sorry. I get really excited talking about numbers. If I didn't become an architect, I would have become something related to numbers, actually. And uh, as a logical thinker, numbers. What I love about numbers is there's like some sort of definition to things, and you can apply these definitions in design solutions. So I'm gonna end this video here. I've rambled on for quite a bit. Uh, I hope you guys enjoyed watching. I hope you always take care of yourselves. I hope we can always better ourselves. And until next time, bye bye.